see in the other examples. This is for illustration. Look at the portion of the Smith chart. On this Smith chart, point number 1 is find out what is YL. So once you know what is YL, then we will find out what is YL in. So from YL you find out what is YL in. That we have found out already. YL in is equal to 0.25 minus J 0.25. So look at that point. How to look at that point? First find out G is equal to 0.25 circle. So constant G circle. Then find out the constant susceptance R, which is 0.25, where they meet each other. That point is the YL in. So as we have done in the last class, in this class also you find out YL in point. Now once we know what is YL in point, step number 2 is draw the constant VSWR circle. How to draw the constant VSWR circle? Take the center of the Smith chart as the center of the circle, then draw a circle of radius R such that R is equal to the radius is equal to the distance from the center of the Smith chart to the normalized impedance point. So draw a circle. This circle, this dotted circle that you can see, or the dashed circle that you can see, that will intersect the G is equal to 1 circle. Why it is G is equal to 1 circle? As we discussed, we have to move from the load to a distance L along the main line, such that after the distance L, the resistance is equal to 1, which means the conductance is also equal to 1. R is equal to 1 by G. R is equal to 1 means 1 by G is equal to 1. So G is equal to 1 circle, it has to intersect. It will intersect the G is equal to 1 circle at 2 points. So note those 2 points where it intersects the G is equal to 1 circle. So those points you can see on this Smith chart. You can see on the upper plane, upper half of the Smith chart, it intersects that point at a point 1 plus J 1.57. On the lower half, it intersects that point, that circle, G is equal to 1 circle at 1 minus J 1.57. So these are the 2 points where it intersects the normalized G circle. Normalized G is equal to 1 circle that will be intersected by the constant VSWR circle at those 2 points. Now look at what are the values of the wavelength, values in terms of wavelength of these points. Point number 1 is YLN. So if you join the center of the Smith chart to the point YLN and extend it, that will meet the rim of the Smith chart at a point. So from that point come to the open circuit end. So the distance between open circuit and that point, and that distance is 0.041 lambda G. So that is the distance. Once you measure it on the Smith chart, you will see that open circuit is at 0.5, and whatever is the distance for this point that you find out, so they take the difference 0.5 minus whatever is the distance. So that will give you 0.041 lambda G. So that you can see in the green, on the lettering, or the green font, or the green part shows you that. Now you know green part shows you wavelength towards the load. Because we are using Smith chart as an admittance chart, so the green shows you wavelength towards the load, and the pink shows you wavelength towards the generator. So towards the load, the distance is 0.041 lambda G. Now from the open circuit end, if you move to the first intersection point, which is in the top plane, that distance is equal to 1 point, that is the point of 1.57. So that distance d is equal to 0.178 lambda g. So up to that distance it is 0.178 lambda g. So from the open circuit end to the first intersection point, the distance is 0.178 lambda g. From the normalized load end to the open circuit end, the distance is 0.048 lambda g. So the total length, that is from the normalized load to the first intersection point, the total length is 0.041 lambda g plus 0.178 lambda g. So that gives us d is equal to 0.219 lambda g. So the first, the length of the transmission line from the load. So if you go from the load to a distance of 0.219 lambda g towards the load, towards the source, from the load you move towards the source by a distance of 0.219 lambda g, that is the point where the impedance will be of the form 1 cross j. So that is the point where we should connect the stop. So that is one point. We can find another point because there are two intersections, there can be 2 points. Then we can find another point. When we will require the another point? If this distance is very small, if it is very close to the load, it is very small, then we require a longer path. So practical path length, practically it is very small, we cannot connect it there, then we require a other point. So both the points we should have, whichever is convenient we can use that. The other point, for the other point, the length from open circuit to the other point is 0.322 lambda g. So 0.322 lambda g plus 0.041 lambda g is the total length from the load onto the further intersection point for 1 cross JB. This will be 1 minus j 1.57. So that will be equal to 0.363. So if we add them, that will give us 0.363 lambda g. So d can be equal to 0.219 lambda g or 0.36 lambda g. Whichever one is convenient, that we can take. So that gives us the distance d or distance L. L we have found out, L or d. Now what is remaining is the stop length. So we have to find out the stop length. And so analytically I am not finding it out. So forget this. Then find out what is the stop length. Now for the stop length, we have found out what is the impedance at the A dash point. That impedance is 1 plus minus 1.57. Let us take minus 1.57. So longer distance, let us take 1 minus 1.57. The stop is short circuited. So from short circuit, we have to go to the point 1.57. Minus 1.57. So from the short circuit, we have to move towards the generator, right? And so move towards the generator from short circuit. Short circuit is at a distance of 0.25 lambda g. From the open circuit, that we know. So from the short circuit, the distance to the point 1.57 is 0.9 lambda g. So we will move a distance of 0.9 lambda g from the short circuit. That is, the length of the stop should be 0.09 lambda g. If the distance of the stop is 0.09 lambda g, so Ls is equal to 0.09 lambda g. Find out what is Ls. Ls is equal to 0.09 lambda g. So that you find out from the Smith chart. Similarly, for the upper one, we can again move up to the upper one, whatever is the distance, add that to 0.09 lambda g. Okay. So this is one example. Then we'll come to the next example. This gives you the complete solution. So D or L is equal to 0.219 lambda g, and Ls, length of the stop, is 0.09 lambda g. So this is the solution for this is one example of a solution. Then we'll look at another example. Here we have a transmission line whose characteristic impedance is 50 ohm. It is terminated on a load of 15 plus J25 ohm. We are required to find out what is L and what is Ls. So these are the two things that we have to find out. Now on ZL is 15 plus J25 ohms. Therefore, normalized impedance small ZL is equal to R plus JX, that is 0.3 plus J 0.5. How you find it out? ZL by Z0, which is 15 by 50, that is 0.3, R is equal to 0.3. Then 25 by 50, that is 0.5. So that we get. So first point is find ZL. ZL is equal to 0.3 plus J 0.5. So if you have a Smith chart, then take the Smith chart out and do this. Find ZL is equal to 0.3 plus J 0.5. Then locate ZL on the Smith chart. How you will locate ZL on the Smith chart? You can do that easily, very easy. Look at the constant R circle for which R is equal to 0.3. Then look at the arc which is 0.5. So look at the rim. In the rim 0.5 will be written. So follow the arc which is connected to 0.5. That will meet the small r is equal to 0.3 circle at a point. So that point is your ZL, small ZL point. Then we have to find out what is YL. After you find out ZL, then we have to find out what is YL. Now once you find out ZL, draw the constant VSWR circle as we have discussed up to now. Take the center as the center of the circle, take the center of the Smith chart as the center of the circle. At the center of the Smith chart, R is equal to 1, small r is equal to 1. On the horizontal axis, look for the point corresponding to small r is equal to 1. Take that as the center of the circle. Then draw a circle whose radius is from center of the circle to the point ZL. So draw that circle, that is the constant VSWR circle. So that you can do if you have pencil and compass ready with you. Draw this circle. So let me give you 3-4 seconds. It will take only 5 seconds to 10 seconds. So draw this circle. Let us do it step by step so that it will be easier for you to understand how it is done. Let me give you 5 seconds or 10 seconds to draw this circle. And now locate the point at which this circle is meeting the horizontal axis on the right hand side. That is the VSWR. Either do that or locate the point on which it is meeting the horizontal axis or horizontal line, straight line at the left hand side. From that point, drop a perpendicular to the circle, to the lines which are to the scale which is below the Smith chart. So draw a circle, draw the perpendicular. That perpendicular will give us the VSWR, that will be 4.2, and it will give us the reflection coefficient which is 0.6. So drop that, and so that will give us VSWR and reflection coefficient. To determine what is the VSWR and what is the reflection coefficient for this load, 15 plus J25 load, we find out what is the VSWR, what is the reflection coefficient. Do this, take about 10 seconds. So let me give you 10 seconds. So drop this line and find out what is VSWR and reflection coefficient. So drop this and read it on this scale. So let me show you how to read this. Go to the next one. Next slide. Here on the scale where it meets, look at the SWR scale and look at the reflection coefficient scale. There you can read the values. We have shown you the values, how to read these values. So you can read these values. VSWR will be 4.2, reflection coefficient will be 0.62. Now that you have read the VSWR point and reflection coefficient, both these values you have read, then mark the Vmax point on the resistance line at a point where VSWR circle crosses it on the right hand side of the Smith chart. So mark that as Vmax. The numerical value at this point is also indicative of the VSWR or max that I have told you. The point diametrically opposite to it is the V mean point, and it is numerically indicates the value R mean, which is 1 by VSWR. So the left side gives you 1 by VSWR, right side gives you VSWR. So right side gives you V max point, left side gives you V mean point. How to find out where Vmax will occur, that we have discussed earlier. From ZL, find out what is the distance in terms of wavelength. So if you move from ZL in the clockwise direction to reach Vmax, find out what is the distance that you have moved from the outer rim. So that will give you the distance that you should move from the load to reach the maximum voltage. Then continue in that direction till you reach the V mean. So that will give you the distance where you will get V mean. It is much more easier that you go from ZL to Vmax. So whatever distance you have got, add 0.25 to that. That will give you the distance for V mean. Because Vmax and V mean are located lambda by 4 apart, and you know half a circle on the Smith chart is lambda by 4. So and Vmax point to V mean point is actually half a circle. So undo this. Then once we have got our ZL, we need to get what is YL. We are doing a Smith chart calculation using shunted circuits. Since we are using a shunted circuit, we need to find out YL. So what we will do is, we will draw a straight line. So I draw a line which is passing through ZL, and that we have found out at the center. So draw this red line that you can see. Draw this red line. Draw a line which is passing through ZL and YL crossing the chart at both the ends. So draw a straight line like this. Now the diametrically opposite point of ZL gives us YL. So you can find out what is YL. ZL we have found out. ZL is equal to 0.3 plus J 0.5. Diametrically opposite to this is YL, that is equal to G minus JB, that will be equal to 0.9 minus J 1.45. Just read those values. For YL, read the value of R. So that is YL, through YL, the circle that is passing through YL, that is 0.3. So the complete circle, complete resistance circle that is passing through YL is giving you 0.3. It will be actually 0.9. It will be actually 1 by 0.9. And since we are considering G, therefore it will be 1 by 0.9. So you will find out what is Y. That will be 0.9 minus J 1.45. So look at what is YL. Then observe the line from the center through YL to the outer circle of the chart. Where it meets the outer circle, note the wavelength mentioned at that point. So YL, so suppose YL is equal to Q times lambda. Here you will see that Q is equal to 0.3. So the line, red line has been extended to the rim. There we are noting the wavelength. Wavelength will be in terms of lambda L, that is Q times lambda L. So this is mentioned of the outer circle at the crossing point. So what is that value? That value is 0.33 lambda. So note that value. 0.33 lambda is the value that you can see on this Smith chart. It is 0.33 lambda. Note that value. Then we'll go to the next step. And then draw the unit real circle. Unit real circle means the circle corresponding to R is equal to 1 or circle corresponding to G is equal to 1. So draw that circle. So that is the unit real circle. So take 10 seconds to draw this circle, unit real circle. So what we have done up to now, while you are drawing this, let me repeat what we have done. We have found out ZL, then we have done VSWR circle, we have found out what is VSWR, what is the V max point, what is the mean V mean point. We have extended a line through ZL and the center of the chart to find out what is YL, and the line has made the outer side of the Smith chart are 2 points. Along the YL side we have found out where it is crossing the Smith chart, that in terms of wavelength, that is 0.33 lambda. Up to that we have done. Now we have drawn the unit real circle. So you are drawing the unit real circle. After 10 seconds, you will take 10 seconds to draw the unit real circle, or maybe more, because you have to draw this, you have to find out the center of it. So let me give you half a minute, 30 seconds to draw this circle. So how to draw this circle? Center of the chart, then the end of the right end of the chart. These are the 2 points. Find out the center of these 2 points, or the center of the line joining these 2 points. That is the center of the unit circle. So then you draw the circle. So take half a minute for that.
Can I go to glass there?
Okay, now on that you have drawn the unit circle. Now let us move to the next point. Find out the points where the unit circle is crossed by the VSWR circle. That those 2 points are shown here by the red marks. So from point YL, move on the Smith chart or on the VSWR circle in clockwise direction towards the generator to get YL at its intersection with the unit circle. Also do that. So start with YL, move to find out Y1, which is equal to 1 plus JB1, that will be equal to 1 plus J1.5. So extend a line from the center through Y1 to the outer circle of the chart. Note the wavelength lambda 1, which is equal to P times lambda. That wavelength is 0.18 lambda. So note that wavelength. So we have noted one wavelength 0.33 lambda. The next wavelength is 0.18 lambda. So note that wavelength. Then go to the next point. Note that the susceptance B1 of Y1, and so B1 is equal to 0.15. B1 is equal to 1.56. So note that. Find the admittance Y2 of the socket stop at 1 minus Y1, which will be minus B1. Locate Y2 on the chart as minus JB1, which is equal to minus J1.56. So Y2 is equal to minus J1.56. This will be on the outermost R circle. Outermost R circle is R is equal to 0. Extend the line from the center through Y2 beyond the outermost chart circle. Then note the wavelength Y2 is equal to S lambda. That will be mentioned. That will be mentioned on the outer circle. So that you will do move towards the generator and note that Y2. Y2 is equal to 1.56 minus 1.56. For minus 1.56, the wavelength is that you can see 0.34 lambda. So note that. Do this, take about 10-15 seconds and do this. Now you can find the position of the stop, which is L. This is from YL to Y1, move in clockwise direction from YL to Y1. So L is equal to 0.5 minus Q lambda plus P lambda. Q, you know what is Q, we have found out. What is P, we have found out. So that will give us 0.35 lambda. So that gives us the L1, or the length of the position of the stop. That is A dash point to from B to A dash. That length is this 0.35 lambda. Find out this. Then next is finding out the stop length. So for the stop load, you know load is short circuited because we are using a short circuited stop. You can use an open circuit stop. Here we are using a short circuited stop. So for the stop load is short circuited. Y2 is to be towards generator because from the load we are moving towards the transmission line. So that is towards the generator. And so we are moving towards the generator. Find the length of the stop L2. That you will do by moving from short circuit to Y2 in clockwise direction. Clockwise direction is because we are moving in the towards the generator. So L2 is equal to S lambda minus 0.25 lambda. S we have found out, put that value. So this will give us 0.341 lambda. So that completes this design using Smith chart. This completes the design. So stop matching, single stop matching, we have discussed one example. Next example I will give you as homework. Since there are not many people, so we will take it as an example. Homework. So match ZL is equal to 90 minus J 120 ohms with a line of Z0 is equal to 75 ohms. This is a homework. Follow the same principle that we discussed and do this. Next class, what is the time? Okay. So you will use again short. I will tell it very briefly. You will do it yourself. So let me take a break here. Then I will come back and tell you very briefly. You will do it yourself.